Hey everyone, welcome back to The Explainer. Today we're going on a seriously cool trip, a complete macro to micro journey into the world of electrical power. We're going to track this invisible force that literally runs our modern world. We'll start way up high at those massive heavy-duty generation grids and trace it all the way down to the actual dirt beneath your feet. Trust me, by the time we wrap this up, you are never going to look at a wall socket the same way again.
All right, so here's our game plan for today. We're going to kick things off with the physics of three-phase power, then look at how the entire grid is connected up. After that, we'll dive into the rules for electrical installations, unpack exactly why earthing saves lives, and finally decode the different types of earthing systems out there.
So, let's jump right into part one, the magic of three-phase. We're starting big here with the macro mechanics.
Now, standard domestic electricity, usually single-phase. But step into almost any commercial, industrial, or transmission setup, and it's all about three-phase power. Why? Well, it's insanely efficient. You can push roughly 3 times the power of a single-phase system, and get this, you only need one extra wire to do it. Plus, it gives you constant power delivery. It completely wipes out those peaks and dips that you get with single-phase circuits. Because that flow is so smooth, it's absolutely crucial for running heavy industrial equipment. And honestly, it all boils down to cost effectiveness. Less conductor material needed, way more efficient generators and motors, it's a no-brainer.
To really wrap your head around that constant power delivery idea, take a look at these smooth intersecting sine waves. In a normal single-phase system, the voltage drops to 0 100 times a second. It's like a pulsing effect. But here, because they're separated by a 120-degree phase angle, whenever one wave dips, another one is peaking. It is just a relentless, uninterrupted push of power. And the math completely backs this up. The power formulas for both star and delta connections show exactly how this setup maximizes your voltage and current efficiency.
And this brilliantly illustrates the 2 main ways engineers actually harness those 3 phases, the star or Y connection and the delta connection. Look at the physical layout here. With the star connection, your 3 phases meet right at a central neutral point in the middle, which gives you both a line voltage and a lower phase voltage. But then contrast that with the delta connection. They're wired in a closed, continuous loop. That setup delivers massive, uninterrupted torque, which is exactly what heavy motors crave. It lets engineers perfectly balance the loads to keep equipment totally stable, as you can see in the quick calculation example right here.
Moving on to part 2, connecting the power grid. So we have all this immense power, but how does it actually get organized before it hits a building?
Let's use the Sri Lankan power system as our roadmap here. Think of me as your tour guide as we work our way from top to bottom. Up at the very top, we've got generation, pushing power out at 12.5 kilovolts. That immediately gets stepped way up into these massive grid substations. We're talking 220, 132, or 33 kilovolts just to survive long-distance travel. As we follow the lines down, check out the 33 kilovolt feeders crossing over provincial borders. Eventually, that power hits primary substations where it's stepped back down to 11 kilovolts, and then it filters through distribution transformers right down to the everyday low-voltage consumers at the very bottom. It's an incredibly structured hierarchy.
Now, what's really interesting about this setup is how consumers get categorized based on their appetite for power. The magic number here is 42 kilovolt amps. If your building needs less than that, you just get an ordinary supply from the standard grid. Simple. But the second you cross that 42 kVA threshold, boom, you are now a bulk consumer. And if you're a heavy industrial user pulling more than 2 megavolt amps, the utility just hands you the 33 kilovolt line and says, good luck, you are entirely responsible for building and maintaining your very own substation to safely step that massive voltage down.
All right, part 3. Rules for electrical installations. With all of this raw, immense power flowing right into our communities, who is writing the rules to make sure our buildings don't just, burn down?
Well, it turns out regulating electricity is very much an evolving science. The whole thing kicked off way back in 1871 when the Institute of Electrical Engineers, or IEE, was formed. Fast forward to 2006, they merged to become the IET. And their absolute Bible for safety is the BS 7671 wiring regulations. We are currently sitting on the 18th edition, which came out in 2018. These rules are constantly being updated, and they cover everything. They're designed to protect people, properties, and yes, literally livestock. Because let's face it, a cow out in a field is just as susceptible to a stray voltage shock as you or I am.
Just look at this literal stack of safety iterations. It is a rainbow of regulations. Every single color you see represents a totally new edition of the IET wiring regulations. Because as our technology advances and as we uncover new hazards or learn hard lessons from fires and shocks, the BS 7671 standards have to evolve to meet them. It is quite literally a shield of paperwork standing between us and raw electrical energy.
Which brings us to part 4. Why earthing saves lives. This is where we get into the micro-level stuff. How do these massive regulatory standards actually keep the electricity in your living room from killing you?
I really want you to pause for a second and think about this. The electricity hiding right behind your walls is constantly trying to get to the ground. It's this immense, invisible pressure just waiting. So if a wire frays or the metal casing of your washing machine accidentally becomes live, what actually happens next?
So the crucial point is right here. Without earthing, if a live wire touches a metal casing, the entire body of that appliance is suddenly at a very high voltage. If a person happens to touch it, well, their feet are at 0 voltage on the floor, right? So a fatal red path of fault current rushes directly through their heart and body to get to the ground. It's a worst-case scenario. However, with earthing, that metal casing has a dedicated low-resistance wire going straight into the dirt. When someone touches it, the electricity basically ignores them entirely, taking that path of least resistance right down the earth wire instead.
The fundamental physics at play here is actually pretty elegant. The Earth itself, the literal dirt, rock, and soil outside, acts as this massive, practically infinite conductor at absolute zero potential. By physically hardwiring the exposed metal parts of our appliances to the general mass of the planet, we totally neutralize the voltage difference. We're essentially building a superhighway for fault currents, pinning the equipment's voltage as close to zero as humanly possible, completely neutralizing the threat.
All right, let's move on to our final stretch, Part 5, Types of Earthing Systems. We know the physics, so let's see how this builds into real-world engineering and the exact methods used to connect our homes to the Earth.
Before we dive into the schematics, we need to decode the alphabet soup that BS 7671 uses to categorize these systems. The first letter always tells us about the power source, and the second letter tells us about your specific building's setup. So T comes from terra in French, meaning a direct connection to the actual ground. I stands for isolated, N means neutral, as in connected to the supply network's ground, and C and S just stand for combined or separate protective and neutral wires. Keep this vocabulary tucked in your brain for a second.
Okay, let's look at a TT system. Remember our letters. That first T means the power station generator has its very own direct connection to the Earth. The second T means the consumer, so your house, has its own completely independent local Earth electrode. This is usually just a solid copper rod driven deep into the dirt outside your window. In a TT setup, the source and the load don't share a ground at all. They are totally independent. The only things the utility company is sending down the line to you are the live and neutral wires.
But there is a catch with the TT system. Because you're relying entirely on the local dirt in your backyard for your safety path, the fault loop impedance can actually be quite high. Let's be real, dirt isn't a perfect conductor. This means a dangerous earth fault might not actually generate enough current to flip a standard old-school circuit breaker. So, TT systems bring in a highly sensitive bodyguard called an RCD, or residual current device. Here's how it works. Step 1. The RCD constantly monitors the current going out on the line and coming back on the neutral. Step 2. If power leaks to an earth casing, it creates a tiny imbalance. Step 3. The RCD detects that discrepancy in a fraction of a second and instantly severs the circuit.
Look closely, right at the moment a fault happens. The normal path of electricity suddenly leaks out down into the installation earth. The literal microsecond that happens, the returning neutral current drops slightly below the outgoing live current. The RCD immediately senses that the scale is unbalanced and just throws the breaker open. It acts so fast that it saves your life long before a lethal shock can even be delivered.
Now let's contrast that TT setup with the TN system. Again, let's use our letters. The first T means the power source is earthed, but the second letter is N for neutral. In this setup, the utility company doesn't just send you power. They actually supply the grounding path directly into your house through a protective earth wire, or PE. You aren't just relying on a copper rod jammed into the dirt out back. You are physically hardwired straight back to the massive, highly reliable grounding system of the power station itself.
Because TN systems rely so heavily on the utility's cables, there are 3 main flavors you'll see out in the wild, based on how the utility decides to run the wires.
First, there's TNS, where the protective earth and the neutral are kept as completely separate wires all the way from the power plant to your wall. Then there's TNC, where they are combined into one single shared conductor. And finally, TNCS. Here, they start off combined leaving the power source, but the moment they hit your building's distribution board, they get split out into separate protective and neutral wires to safely run your appliances.
Man, we have covered a tremendous amount of ground today. We started way out with the sheer mathematical force of three-phase power spinning inside those massive generators. We tracked it through high-voltage grid layouts, saw how it gets reined in by constantly evolving safety standards like BS 7671, and finally zoomed all the way in to see how ingenious earthing setups and RCD switches act as this incredible invisible shield of engineering. Every single day, these systems are flawlessly funneling deadly forces safely into the earth right beneath us.
It really is an absolute masterclass in physics and safety. So I'm going to leave you with this final thought. The very next time you plug a heavy metal-cased appliance into a wall socket, just take 1 second to look at that third grounding pin. Ask yourself, do you know if your house is running on a TT or a TN system? And more importantly, is that invisible lifeline truly secure? Thanks so much for hanging out with me for this explainer. Keep asking questions and keep learning.